Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. This video is the first video in a short course on group theory. Now, groups are fundamental objects in mathematics, and they were invented by Galois in the 19th century to show that the quintic equation can't be solved the same way that the quadratic and the cubic can be using a formula using radicals. So the key to this was analyzing the symmetry in the roots. And that's where the group theory comes in. So more generally, the notions of group theory and symmetry are very closely tied together. And in fact, a lot of mathematicians tend to conflate these two notions. So what we're going to do in this video today is we're going to motivate the definition of groups by looking at symmetry from a mathematician's viewpoint. Okay, so to start, I'm going to have a look at some examples of asymmetric and symmetric objects so that you can see what we mean by symmetry and how we can express it mathematically. Okay, so here we've got two plane figures. Here a quadrilateral like this, that's asymmetric, and here we have a square which is a very symmetric object. Okay, so why is this square symmetric? Well, I guess one thing you can say is that it has a symmetry about this vertical axis here right down the middle. So here's a line L1, and it's symmetric about this axis. It's also symmetric about a horizontal axis like this. And it's also symmetric about the diagonals as well. So here's L3 and L4. Of course, all the lines should go through the center of the square here. I've missed it here. Okay, so what other symmetries do you have? The other symmetries you have is that, well, if you rotate this square 90 degrees, it will look just the same as before, okay? You can also rotate it 180 degrees or 270 degrees, and it will look just the same as before, okay? So the way that mathematicians want to look at the symmetries here are as follows, okay? So you certainly have rotations about angles pi on 2, pi on 3, pi on 2, and also we'll say rotation by 0, which is just the identity. Okay. The other thing is, what about the reflections, the symmetries that you see about these axis lines? Okay. So the way we want to think of them is we want to think of these reflections as actual maps of the plane to itself. Okay. So the maps from the plane to itself, and they're the reflections which have these lines as axes of reflection. So we have 4 reflections about the lines L1, L2, L3, and L4. So in each case, the symmetries, as we want to think of them mathematically, are maps of the plane back to itself, and they take the square back to itself, so it looks just the same. Okay, so that's one example, example A. Let's move on to a completely different example. That's the following here. Here we have 2 polynomials in the variables x, y, and z. This one here is asymmetric, and this one here, x squared plus y squared plus z squared, looks very symmetric. Okay, in what sense is this symmetric? Well, it's symmetric in that the roles that the x, y, and z play, they all look similar. Okay, they play the same role. They're symmetric in the variables. Okay, so how can we express that symmetry in a mathematically sound way? Well, one thing you can do is you can swap the variables around. Like you can swap x and y. Okay, if you replace the x with y and y with x, you get y squared plus x squared plus z squared, but as a polynomial, it's the same as this polynomial here. Okay, so one way to express the symmetries is to look at the 6 ways of permuting these 3 variables x, y, and z. Okay, and that's how we express the symmetries of this polynomial here. And the final example that I want to have a look at, which is extremely important in physics, is looking at space. Okay, so suppose here I am, a fixed observer in space. Of course, if there are lots of objects around, you have an asymmetric situation. But let's suppose now we have empty space. We remove all the objects from space, okay? And then to the fixed observer, like I'm standing here, space looks all the same. It doesn't matter whether I look at it up that way, or in another direction, okay? So in particular, if I rotate my head in a certain direction, it looks the same. Or equivalently, if I rotate the whole of space around me, it will look the same, okay? So in this case, the group of symmetries here, set of symmetries are all the three-dimensional rotations, okay, about the fixed observer. So they're the elements of the special orthogonal group in three-dimensional space, SO3. Okay, so I hope you've got a bit of a sense of how mathematicians think about symmetry. Okay, and in each case, what are the things that they look at? Okay, in each case, it turns out that the things that we look at here, we look at ways of permuting x, y, and z. Here we look at maps from the plane to the plane. In fact, you just swap points in the plane, so you're just permuting points on the plane. And here we're moving, we're rotating, so we're just moving points in the plane around, so we're just permuting the points inside R3. So the basis for defining symmetry is something called the permutation group. Okay, so let me introduce that for you. We start with S is some set, okay, and we can define the permutation group on S. Okay, so what is the permutation group on S? It's basically all the permutations of the elements of S. So in other words, more precisely, they're all the maps sigma from S to S, such that sigma is bijective, both one-to-one and onto. Okay? So the elements here describe all the elements of the symmetries inside here. Okay? Of course, you'll get lots more, and this is a much more general setup. And what we want to do is we want to bring in some algebra. Okay, so let's make some remarks about this set. So this set has some special algebraic features. Okay, so suppose you have two permutations, sigma and tau of S. Okay, so two bijections from S to S. Okay, so what you can do is you compose these. So these are just functions from S to S, and you've got another one from S to S. So composing will get you a function from S to S. And of course, the composition of two bijections is a bijection. So actually, you'll get a permutation of S. The composite of two permutations, sigma and tau, is again a permutation. Okay, so sigma here, so that's the first point. The second point is sigma is bijective, so it has an inverse. Okay, and its inverse is a function from S to S, which of course is bijective. So sigma inverse is also a permutation. Okay, so the algebra comes from the fact that now we've looked at composition, it's like some sort of a multiplication, and we've looked at an inverse here. And the last thing is, well, do you ever have permutations? Okay, can it be empty? Well, the answer is no. You've always got the identity map from S to S. And that's usually denoted in group theory with a 1. And that's always a permutation we have of any set. Okay, so these things here are important to keep in mind, and to a certain extent they capture a bit of the notion of symmetry. So let me just try to suggest why that's the case, okay? So when you're talking about symmetry, you're saying more or less that, for example, rotation is symmetry. When you rotate it, well, you get the same thing. Okay, so if you get the same thing, you should be able to rotate it back. Okay, so that's why you also want the inverse in there. Okay, so now we've defined the permutation group, which gives the ambient environment in which to talk about symmetries. To talk about symmetries of an actual object, we need to look at subgroups of the permutation group. So let me define that for you right now. Okay, so suppose we have this set S and we consider its permutation group, the set of all bijections from S to S, and we have a subset G of that. Okay, we say it's going to be a subgroup if it satisfies the following three closure axioms. Okay, so what are the closure axioms? Suppose you have two elements inside this group, so it's two permutations of S inside G. Of course, the composite is also a permutation of S, and we want that permutation to be inside G as well. In other words, G is closed under composition. The inverse of sigma is also a permutation, and we want G to be closed under inverses. In other words, sigma inverse should be in G for all sigma in G. And finally, remember, the identity on S is a permutation, and we want that to be inside G as well. So this is closure under the identity. So a subgroup of this permutation group on S is just a subset which satisfies these three closure axioms. And if we have such a subset, we write G is less than or equal to the permutation group on S. Okay, so that's the definition, and this is how mathematicians think of symmetry. So let's see how our examples fit into this framework and definition. Okay, so let's look slightly more generally. So before we looked at the symmetries of the square, let's look at a regular n-gon R inside the Euclidean plane P. Okay, So what's the symmetry group of this regular n-gon? Okay, so another name for this that mathematicians use is the dihedral group of order 2n. Okay, so remember the way we thought of that for the square we had the 4 reflections about the axes of symmetry, and then we also had 4 rotations as well. Okay, so we want a slightly more abstract definition, and that's the one here. Okay, so what does this dn, this symmetry group of this regular n-gon? So remember the basis of how we want to describe it is we want to look at permutations of the plane. Okay, so we want to look at the certain permutation sigma inside this permutation group. And which ones are they? We basically want the isometries of the plane which take R back to itself. So in other words, sigma is going to be mapped from P to P, which preserves distances, and also sigma of R is equal to R. Okay. So I claim firstly that this is actually a subgroup of the permutation group of P. So to be a subgroup, what does it mean? It has to satisfy these 3 closure axioms. And it's quite easy to see that it does. Okay, so let me do a couple of them. So firstly, the identity. Does the identity preserves distances? Okay, so if you have 2 points and you apply the identity, they don't move, so the distance between them doesn't change. Okay, what happens if you look at the composition of 2 of these permutations? Okay, well, if tau preserves distances, so when you apply tau, a distance gets to the same distance, and then you apply sigma, that distance doesn't change when you move again. So of course the composite also preserves distances. Also, if tau sends R to R, and then you apply sigma, that still sends R to R, then of course the composite will send R to R. So both these conditions hold for the composite, so this dn is also closed under composition. And it's quite easy to see, similarly, that this subset is closed under inverse as well. So indeed, this is a subgroup of this permutation group. Okay, great. And the other thing to note is that it's quite easy to see using linear algebra that what are the elements inside here. So in general, if you have a regular n-gon, just as we had reflections and rotations before for the square, in fact, you'll get n reflections in general and n rotations. Okay. Now, if you try to check the axioms from this description, actually, it requires you to use interesting facts from linear algebra. So remember, when you compose 2 reflections in the plane, of course, you get a rotation. And of course, if those reflections actually happen to be symmetries of your regular n-gon, then that composite rotation will also be a symmetry of the regular n-gon. Okay, so that's an example, and it shows that the way we looked at symmetries for regular n-gons in the plane fit into this definition here. Okay, so let's look at the third example, example C, that I gave you to motivate the notion of symmetry, and that was SO3, okay, the set of rotations in 3-dimensional space. Okay, so of course each rotation permutes the points of R3. And what are these rotations? Remember, they're also just the orthogonal matrices, which are special in the sense that they have determinant 1. Okay, so I claim that this, which is certainly a subset of this, satisfies these 3 closure axioms, so is indeed a subgroup of that permutation group. Okay, so maybe let's check this other closure axiom here, inverses. Okay, so here, to check that the inverse of something in here, a rotation is clear because you just rotate it the other way. Okay, let's check the composite. The composite is more interesting because when you rotate about different axes, of course, it's not so obvious that you get a rotation. But if you remember, to check that you do get a rotation, all you have to check is that the composite is both orthogonal and has determinant 1. Now, each of these have determinant 1, so the determinant of the composite has also has determinant, the product of those, which is 1. And since these are orthogonal matrices, it's easy to check that the composite is orthogonal as well. So this is indeed a subgroup of the permutation group on R3. And the symmetries of empty space, if you're looking at it from a fixed observer, SO3, okay, does indeed define a subgroup. Okay, so we can put that idea of symmetry into this framework here. Okay. So I want to make an important remark to motivate the definition of a group, which is yet to come. Okay, and it goes as follows. Okay, so suppose you look at this regular n-gon here. What you can do is look at the symmetries of that. So there are various ways you can isometries of the plane, which map this regular n-gon back to itself. And of course, since it's like that, it has to send all the vertices back to the vertices. Okay. So in particular, if you let V be the set of vertices of this regular n-gon, then each permutation sigma in this dihedral group, in this symmetry group of R, will permute the vertices. And in fact, if you know what it does to all the vertices, you know what it does to the whole of the regular n-gon, and hence the plane. Okay? So this sigma is actually determined by how it permutes the vertices. Okay? So here we see, oh, there's an interesting relationship. Okay? So here you'll get, turns out, a subgroup of the permutation group of V. These elements here, which give you symmetries of R, give you a subgroup of a permutation group of P. So of course they're very strongly related, and of course you want to use one to study the other. Okay, so the question is, well, how do you move between the permutation group of V, or subgroups of that, and subgroups of a permutation group on P? Okay, and the key point is that to do that, what we're going to need to do is we need to be a little bit more abstract. Okay, and we need to abstract the algebraic features of what's going on in this setup, and that will lead us to the notion of an abstract group. So finally, we can now give our abstract definition of a group. Okay, so what is a group? It's a set G and also a multiplication map. So we're going to endow this set with an extra piece of data, a multiplication map, and all that is just a way of taking some ordered pair, combining two elements of G which are ordered into a product, another element of G. And the way we'll abbreviate the product is we'll write the product of G and H as GH, like this, but really I guess this is just an abbreviation for mu of GH. So that's the two pieces of data that's used to define a group, and these pieces of data must satisfy the following three axioms as well. Okay, so the first one is the associative law. If you're given three elements of the group G, H, and K, it doesn't matter how you bracket the triple product here. So GH multiplied first times K is equal to G times the product HK with the HK multiplied first. The next axiom is the existence of an identity element. So what does that mean? So there is some element 1 inside this group G which has the following special property. If you multiply by this 1, it doesn't change the element. In other words, 1 times G is always equal to G for any G in the group, and G times 1 is also equal to G. That's the second axiom. And the third axiom is the existence of inverses. Okay, so what's that mean? So that means that for every group element G, there's another group element, I'll denote G inverse, and has the property that you expect for inverses in the sense that G times G inverse is equal to this 1 here, and G inverse times G is also equal to this 1. Okay, so there's a couple of remarks to be made. So the first one is that in this group, if there is such an element which satisfies this, okay, if there is this element 1, then there can only be one possible such element. So this element has to be unique, okay? So it is called the one, okay? And we write this symbol, we haven't chosen it, it's the only one that it can be, okay? So it's unique. So that means that there's no choice when we write that G times G inverse equals, well, could it equal a different one? No, there's only one possibility for what it is here, okay? So the same thing goes for the inverse. The inverse is unique, okay? If there exists an inverse, so another element, such that when you multiply it with the original gives you this 1, then that element is uniquely defined, okay? So we can denote it using G inverse. Okay, so this is the existence of 1, and this is the existence of inverses. And a group is just a set endowed with this multiplication map. Okay, they're the two pieces of data which satisfy these three axioms. Okay, so it may look a little bit funny now, but the key point is that this is the notion which abstracts all the algebra inside this permutation group here. So in particular, this permutation group is an example of a group. Okay, so let's just see how that works. Okay, so to be a group, you not only need a set, you also need this multiplication map. Okay, so of course you've got the set of permutations, and what's the multiplication map here? Mu is just the composition of permutations. So remember, you can compose two permutations of S to get a permutation of S. Okay, that's something that we saw before. Okay, so we've got the data for a group, and now to check that it's a group, you just need to check these three properties here. Okay, so what are the three properties? Let's go through them one by one. So the first one is associativity of multiplication. So here, the multiplication is composition of functions, and of course we know that composing functions is associative. So that checks the first axiom. What about the next axiom? So remember, I told you that the identity map on S is a permutation, and of course when you compose with the identity, you don't change a function. Okay, as long as you can compose with it. So in this case, yes, composing with the identity permutation doesn't change the permutation G. And the last axiom that we need to check, okay, so this one's checked now, is the inverse axiom. Okay, so let's have a look at that. So suppose you have a permutation, we need to check that its inverse in this sense exists. Well, of course, the inverse of a permutation is also a permutation. And the key point is that when you compose a permutation with its inverse, you get the identity permutation. So an inverse in that sense of the inverse of a bijective function coincides with the inverse in this group sense. Okay, so this is the group inverse. Okay, so that tells you that the notion of inverse there coincides with the one here, and in particular this axiom is satisfied. Okay, and that also suggests why this is called the inverse. Okay, great. So we have here now an example of a group, and really in many ways it's the motivating example of the group. The other thing that we should look at are the subgroups of permutation groups. So things like the symmetry group of the regular n-gon, or SO3, or permutations, I guess we looked at permutations of x, y, and z as an example here already. So those two, okay, are they also groups? Okay, and the answer is yes. And I'll answer this in a more complicated way, okay, so to tell you a little bit more about group theory. So we define the notion of subgroups of the permutation group. So that was quite easy. There's subsets of the permutation group that satisfy three closure axioms. Okay, what are the three closure axioms? It's closure under composition, closure under inverses, and closure under the one. Okay, well, it turns out that you can also define the notion of a subgroup of a group, an arbitrary group, not just a permutation group here, of an arbitrary group, the same way using those three closure axioms. They all make sense because you can now replace closure under composition with closure under multiplication. Okay, you can ask that a subset is closed under multiplication. Okay, since you know you have inverses, you can ask for closure under inverses, and since you know you have an identity in a group, you can ask for closure under the identity. Okay, so what happens now? Okay, so we can talk about a group G, and we can talk about subset H, which is a subgroup. Okay, so it satisfies these three closure axioms. Okay, and I claim that this H is actually also a group as well. So all those examples that I showed you, the symmetry group of the regular n-gon and SO3, they're also groups. Okay, but to be a group, remember, you also need a multiplication, a way of combining two elements here to give you an element inside here. Okay, a multiplication map. Well, the key point is that if you have closure under multiplication inside here, remember you can multiply two things. If you have two elements inside H, H1 times H and H2, you can multiply them certainly inside here, and that will give you an element of G. And closure under products means that this element is actually inside H. So we can restrict, in other words, the multiplication on G to a multiplication on H. So multiplying two elements of H will give you back an element of H. Okay, so that gives you a multiplication map. And then you can check whether it satisfies these three axioms. And it turns out that it does, and it's quite easy to check, in fact, that it satisfies these axioms. Okay, so basically you're restricting your multiplication to just putting in elements of H instead of inside G, so the associativity law holds. You're just checking fewer equations here, just checking the equations where all three of these inputs are actually inside the subset H, the subgroup H. The identity inside the subgroup is just the identity of the original group. Okay, so remember, closure under identity says that this is still inside there. And the inverse in the ambient big group G is also the inverse inside the subgroup H. Remember, there's closure under inverses, so that checks that last axiom as well. So we see that this shows us that firstly we have a notion of subgroups of an abstract group G, and all those groups that we looked at before, subgroups of the permutation group, they themselves are groups in their own right, so we can use group theory to study them. I hope you enjoyed this adventure in pure mathematics.